Okay, so 1 minute left. We can start. Which grade? Primary 5, primary 6. So for those who can attend RMO. Okay, maybe we just start. Okay, I mute this. So okay, now yeah. Now this should be the third week of the RMO book B run through, right? So now today is going to talk about the question 21 to 30, which is all about countings. So counting is some topic that maybe not the most difficult, but is those with the lowest scoring rate because it may not be difficult for you to find a way of solving the problem, but there are many mistakes waiting here for you. So it's so easy to make mistakes for kids or even for adults. So to be honest, for me, so counting is the only subject that I cannot justify I'm doing the correct way, unless I see the answers. So I can maybe just run through all the questions without the answers. But for countings, maybe I need to check the answer. So that's the counting part. Okay. So now for RMO, counting, is not that difficult. So, but at least easier than SMOPS. So in SMOPS, focus on counting each year in SMOPS, even the round one, there will be 4 or more questions about countings. So if you're preparing for the SMOPS, APMOPS, you should focus more on countings. For RMO, however, it should be easier, but not that easy. Okay, let's see the questions. So the question one and question 2 is the usage of the plate insertion method. The plate insertion method is used to distribute identical balls. We have some identical balls into distinct boxes problem. So actually we have 4, right? So we have 4 typical type of counting problem. Identical ball to identical boxes, identical ball to distinct boxes, distinct ball to identical boxes, distinct ball to distinct boxes. So 4 type of questions, we have 4 different ways of solving it. And for this, so identical balls to distinct boxes, we always use the plate insertion method, right? So now the question 1 is a very typical one. So we have 8 identical coins, and we want to distribute into 4 distinct bags. And we should make each of it at least 1. So how many ways are there to distribute the coins? So actually, plate insertion is a corresponding way. So if you want to make these 8 coins into 4 different bags, so 1 bag means 1 pile. If we want to divide the whole into 4 piles, maybe we imagine that the 8 coins here, we insert some plate to make it pile to pile. So the problem is, so if we want to divide into 4 piles, how many plates do we need to insert inside? Must be 3, right? So Now, if we want to divide them into 4 bags, so we need 3 plates to be inserted. Inserted where? So the plates is to divide balls or coins apart. So we need to insert the plates into the intervals made by those balls. So we have 8 coins, which means there are 7 intervals. So now the question becomes, right? So instead of dividing a coin into 4 bags, it becoming inserting 3 plates inside 7 intervals. Obviously, so 2 plates cannot be put in the same interval, right? So then the method would be just to choose 3 plates from the 7 intervals. So the answer is just 35. And this 35, one method of inserting plates, just responding to one method to distribute coins. For example, if we insert 2 plates here, so which means A for 2, B for 2, C for 1, and D for 3, and so on. So now this is the so-called plate insertion method. And you may notice that the plate insertion method, it basically is to solve identical ball into distinct boxes, and this way of inserting plates will ensure that each plates get at least 1. To remember, this is the basic requirement of the plate insertion. So each plate, or each pile contain at least 1 coin, 1 balls. So if it requires some pile to have more than 1 or can be 0, so we can adjust the number of balls to satisfy the need. So for example, we are going to see the question 2. So question 2, it says that we have 10 different dishes in a buffet, and we have only 4 plates. So the plates must be the same, right? So actually, so the logic is like, so we want to distribute the 4 plates we have to the 10 different dishes. Of course, right? So now plates have a fewer number than dishes, which means we cannot pick all the dishes. So each of the dishes can be 0. Also, right, it says that so the plates can be empty as well. So firstly, let's ignore this. We ignore this condition. So if the plates cannot be empty, okay, so we just solve an easier question. So if plates cannot be empty, so we must use up all the 4 plates. So it's just like distribute 4 plates into the 10 distinct dishes. We want to do the plate insertion. However, so the plates is smaller than the dishes. So each can be 0. So how to solve this can be 0 problem? So as long as we see a can be 0 problem, we can borrow a ball to the plate, to the dishes. So how do we check this? So now the case is 4 plates or 4 balls to 10 boxes. Each can be 0. So 0 is 1 less than 1. So then maybe we just borrow 1 ball to each of the boxes. So there are 10 boxes. Then we borrow the 10 balls to them. So make it there totally 14 balls. So as we borrowed 1 ball to each boxes, then now each boxes would contain at least 1 balls. So this is the way that we can turn the condition into each box containing at least 1. So 4 balls into 10 boxes, each can be 0. It's just the same question as we have 14 balls into 10 boxes, and each box contains at least 1. And now this becomes a typical question as we talked about before. So for at least 1, we can just use the plate insertion directly. So 10 boxes, we need 9 plates. For 14 balls, we have 13 intervals. So the method would be what? So it would be, this is 9. It would be choose 9 from the 13 intervals to insert plates. Also, we should know that choose 9 from 13 equal to choose 4 from 13. And then we can calculate the answer, right? So now, this is if the plates cannot be empty, we know how to solve it. However, so if the question says that if the plates can be empty, how to solve this? Actually, we just need to do a slight change to the thinking. How? So now we have 10 dishes, we have 10 boxes, right? So now if a box can be empty, why not we treat this empty to be another dishes? So maybe if a place is empty, we can treat that as for the air, right? It's for the air. So we call empty a dishes as well. So empty is one kind of dishes. So which means, so if a place can be empty, we can treat it like we still have 4 balls. But instead of 10 dishes, we actually have 11 dishes, 11 boxes, right? So the 11th is for empty. So now we have 4 balls distributed into 11 boxes. Also, each box can be 0. Then, as there are 11 boxes, so we need to borrow 11 balls instead of 10 balls. So it's the same thing as distribute 15 balls into 11 boxes, and each can be, at least 1. And then the final answer would be, so we have 14 intervals, and we need 10 plates to place the plates. So it's equal to choose 4 from 14 as well. So and then the answer is just 7, 11, and 13, which we should all remember the number. So it's 1001. Okay, the question 1 and question 2 is all about plate insertion. So each year there will be one question about plate insertion method. So be sure you master this method quite well. Okay. And then, for question 23 and 24, they are something about number theory counting. So this is the hybrid of number theory and counting. This is the SMOPS favorite question. So each year in SMOPS, there will always be such kind of question. So now the question 3, the question 3 is about, we want to form a number from 2021 to 8,999. So we should make how many integers have its sum of digits divisible by 7. So it's about the sum of digit problem, and not the sum of digits equal to a certain number. It's not about the sum of digits equal to one certain number, but question 22. This is question 22. What's wrong with it? If you just want to see it. Okay. So if you just want to make the sum of digit a constant number, for example, sum of digit equal to 10, equal to 11, we can also use the plate insertion to help us. But now, it's not about the actual value. We just want the sum of digit divisible by 7. It's a multiple of 7. So it's quite different. So as we mentioned last week, as long as we see the sum or difference of a certain number equal to something's multiple, we always referring to the remainder problem. So if you want to make the sum of 4 numbers a multiple of 7, then we just want to make sure the sum of the remainder is a 0 or 7 or something like that. So we can use the remainder to help us think of it. But for this question, there are a certain skill to help us solve it. The skill is called the leftover number. Or leftover method. So what's the called leftover method? So now we have 4 digits, right? And this 4 digit, the 1000 digit is a little bit weird. It's not 1000 to 9999. It's 2000 to 8999. So why is that? So this is the hint the question gave us. So maybe we try to start with 2000 to 8999. So not starting from the 2021, but 2000. And you will see that the 1000 digit, right? The 1000th digit is 228. How many numbers are there for 228? Actually, 7 numbers, right? So the 7 consecutive numbers would have a remainder divided by 7 to being 0, 1, 2, 3, 4, 5, 6. Each of them exactly once. And this is the hint. So how do we use this? So we can treat the 1000 digit as the leftover number. So firstly, we just let the last 3 digits to be any random number we like. So we have 10 times 10 times 10. We can randomly determine the last 3 digits, right? And then after these 3 numbers are determined, we can calculate the sum of digits. Yeah, we can calculate the sum of digits here. And then after the sum is done, so the remainder should be determined, right? So this remainder would be 0, 1, or remainder 6 when divided by, well, divided by 7, right? And then the 1000th digit is the so-called leftover digit. Because, so we just need to find another number to fit the need, to make the sum of all a multiple of 7. So for example, if the sum of last 3 digits have remained 0, then we make the 1000th digit a 7. If the sum of digit is 1, or the remainder of sum of digit is 1 for last 3, so we make the first digit what? A 6. And so, yeah, in the end, so if the remainder of 6, right? If the remainder is 6, then we put the 1000th digit. No 1 to use, right? So, but we can use the 8, right? For the remainder 5, yeah, we put a 2. Right. So which means, so as long as we determine the last 3 digits, the leftover digit, we have only 1 choices for it. And that's it to say, so from 2000 to 8,999, totally there will be 1,000 numbers that satisfy our need. Meaning the sum of digit equal to a multiple of 7. Right. So now this is the way. However, we should notice that it's from 2021, right? So now we know 2000 to 8999, we have 1000 numbers. What about from 1000 to 2020, right, which is smaller than 2021? So if you want to make sum of digits to be a multiple of 7, so it can be 2005 and 2014. Actually, we have 2 of them. So we just use the 1000 to minus the 2 to get the 998. Okay. So now, yeah, this is the leftover method. So in SMOP, there are 2 questions about this. So one in 2024, one in 2021. So the similar way to use the leftover method to solve a multi-digit number contains. Also in RMO, there are similar questions. So I don't run through this question, but I write it here for you. So the question is, the RMO one is that how many 5-digit numbers are multiple of 7, not 7, multiple of 3, and contain no 3 on its digit. You can think about this question. So it's the same way as the leftover method will tell you. Okay, so now this is question 23. Then we move to question 24. So how many 5-digit numbers are there whose product of digit is 2016? So actually, we just want to make the 2016 into the production of 5 1-digit numbers. You see, so how many ways are there? So we know that 2016 is equal to 5 power of 2, 2 power of 3, and then 7. So it's just we want to divide it into the production of 5 1-digit numbers. So now we can make sure that there must be a 7, because 7 can only appear so long. 7 cannot be into 14 or something, right? So there must be a 7. So the question is about the remaining 4 numbers. We want to distribute 5 2s and 2 3s, into the production of 4 distinct numbers. So there are many ways to do the enumeration, but I suggest you the better way is just you classify with 2 3s. So how can this 2 3s be? So this 2 3s maybe occurs as a 9, or this 2 3s can be separated into 2 3 or 1 3 1 6 or 2 6, right? So we just check. So what form that the 2 3 occurs? So in 1 9, 2 3, 1 3 1 6 or 2 6. And then we just determine the remaining 2s, right? So in first case, we have a 9. So the remaining 4 numbers have a production of 32. So it can be, so maybe we do the enumeration. So it can be 8 4 1, 8 2 2. I write it down here. So if you use the 8, if we don't use the 8, it can be 4 4 2. Right? So now, if 3 occurs as one single 9, there are 3 different ways for the remaining 5 2s. Then, if the 3 occurs with 2 3s, so there are only remaining 2 numbers to make the production 32. So there is only one option, which is 8 and 4. So if it's 3 and 6, then the remaining numbers can be, so the production is 16. So it can be 8, 2, or 4, 4. And then for 6 and 6, so the production of the remaining is just an 8. So it can be 8, 1, or maybe I make it here. 4 2. So actually, this is the way we divide 2016 into the production, right? Into the production of 5 1-digit numbers. Here is the total way, right? Here is the total way. Then, how many 5 digits are there? The second step is that how many ways are there for we to form 5-digit number using these numbers? So actually, if we have 5 distinct numbers for A, B, C, D, E, if we use 5 distinct numbers to form an 5-digit number, the total ways is 5T5, which is 120. However, you see that in many cases, there are 2 numbers there that are the same. So if we use the A, B, C, D, so 5 numbers with 2 of them same. So there should only be, so then we should just choose the 2 place for the 2A. And for the remaining 3 is the 3P3. And then only 60. Only 60. So we just judge by the number to form, by the digit to check how many numbers can be formed. So the first case, all 5 numbers are distinct. So there is 120. In the second case, right, there are two 2's, so they can only form 60, 60, 60. Now this, all 5 numbers are distinct, so 120, 60, 60, and there's 60, so there are 2 6. So making them together, how many? 1, 2, 3, 4, 5, 6. Right, so we have 6 of 60 and 2 of 120. So the total null-digit number can be formed would be 360 to 240. So actually there are 600 5-digit numbers that be formed this way. Okay, so for this question, the most difficult part is the first part, is the enumeration. So how to enumerate it clear enough? So maybe, yeah, you can try my way. So just judge it classified by the form of the 2 3s. Yeah, judge by 3s. If you classify the question by 2s, also you can do, but it become more complicated. Okay. Okay, now this is question 24. And question 25 is the last year's MOPS question. So, and there are many people asked me about this question. So actually, so to solve this question, it's about coloring of rectangle, right? Coloring rectangle. So there is one important skill to solve this question, is that we need to change the counting unit. What's the meaning of this? So it said that we should color each of the grid, right? We should color each of the grid. So maybe you think that each grid is counting the unit. For example, the first grid have 4 options, and then this has 3, right? So we cut. So question 24, yeah, this is question 24. Yeah. So yeah, if we color the grid by grid, yeah, this is the way. But it will be quite difficult to solve this problem. So if we want to color rectangle, so instead of choosing the grid as the counting unit, we can instead choose the column as the counting unit, which means we don't, right? So we don't color the picture grid by grid, but we color it column by column. We treat column as the unit. So now, right, so for the first column, how many ways are there to color the first column? So we have 4 times 3, right? We have 14 ways for the first column. And then we just treat, right? So the coloring may be the A, B, right? So the 4 color A, B, C, D, right? We just treat it to be A, B. Then after the first column is done, so now together we look at the second column, right? The second column. So actually, each column will have 12 ways, but as the first column is determined to be A, B, what about the second column? So now the second column, right? So the first grid cannot be A, so it can be B, C, or D. Yeah, the row 2 can be A, C, and D. So there should be 3 times 3. So 9 possible ways of coloring the second column. But we should notice that it cannot be CC or DD, right? So we should minus the CC and DD. So actually, once the first column is determined, the second column would have 7 ways to color. And then, so when we color it by column, then each column is just depending on the last column, right? So we just need to consider the adjacent column then should be. So as long as the former column is determined, the next column would have exactly 7 ways of coloring. So the second column may have 7 options. What about third column? Also 7, right? The fourth column, 7 as well. Which means if we look at column by column, first column 12, second column 7, third and fourth all 7. So the total way of coloring is just 12 times 7 times 7 times 7. So which is an 4116. Yeah. So notice that if we want to color in a rectangle, we always change the counting unit. We don't color it grid by grid, but column by column. Yeah, for rectangle. Yeah, I write it down here for you to remember. So if we want to color a rectangle, so it's always useful we solve the problem column by column. Yeah, sometimes row by row. Row by row and column by column, they're the same, right? Yeah, so just ignore it. Okay, now this is the top 5 questions. Yeah, top 5 questions. Then the question 26. Yeah, it's very complex questions, I have to say. So it says how many rectangles are there without any shaded areas? So yeah, normally if we want to calculate something without something, yeah, we can think it in a controversial way. So by calculate how many square rectangles are there that contains those shaded regions. So this is about a figure counting using the permutation and combination. So the first thing is, so we can use the permutation and combination to calculate the total amount of rectangles. How do you do this? So actually, no, I changed it to red. So the total amount of rectangles so in the whole figure. So a rectangle is formed by what? A rectangle is always formed by 2 lengths and 2 widths. So first, we just choose from the 1, 2, 3, 4, 5, 6, 7, 8, right? We choose from the 8 horizontal lines, choose 2 from the 8 horizontal lines to be the length. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So then we choose 2 vertical lines from the 14th to be the width. So once we determine the 2 lengths and 2 widths, a rectangle is determined. So this is the way we calculate the total number of rectangle in the whole figure. And this should be, so this is a 28, and this is a 91. So 91 times 28. 2548. Yeah, 2548. Yeah, 2548. Okay. Then, yeah, we just use the total to remove those contain the shaded areas. The shaded areas have 3 small grid, A, B, and C. So then, how to calculate the rectangle contain the A grid? So it's a similar way. I use the different color. So for those who contain A, we just, right? If you want a rectangle to contain A, we just want to make the 2 lengths and 2 widths at both sides of the A. So for example, the top length should be above this A, which means we have only 3 choices. And the bottom length should be below this A, which we have 5 choices. And for the width, it's the same, right? So the left side should be on the left of A, and the right side should be at the right of A. So it's 3, 5, 5, 9. So this is what? So it's 6, 7, 5. Yeah, 6, 7, 5. So for those rectangle who contain A, so the total number is 675. Then, yeah, A and B is symmetric, right? So A and B is symmetric. So those containing B should also be 675. And for those containing C, yeah, it's the same logic. So the top length is above C, which have 5 choices. The bottom length is below the C have 3 choices. And the left side should be on the left, and the right side on the right. So all of them have 7, right? We have 7 options for both left and right. So in total, we should have, so 15 times 49. So this is 735. Yeah. So then we can calculate those who contain A, contain B, and contain C. But can we just use, right? Can we just use the total minus the 675 minus, so remove those contain A, those contain B, those contain C. Is this the final answer? Is this the final answer? Obviously no. Why no? Because there should be crossovers. So in counting, so there will always be crossovers, which is easy for us to make mistakes. So we just calculate those contain A, contain B, contain C. What about those contain both A and B? Right? So we counted it twice. So we minus it twice. So we need to add it back, right? So then we need to calculate those contain both AB, AC, and BC. So first, for those contain A and B, yeah, we just put it aside. So for those who contain both A and B, then A and B, so the top, bottom, yeah, it's 3 and 5. And then for left and right, so left should be on the left of A, right should be on the right of B. So it's 5 and 5. So it's 3, 7, 5. So contain both A and B. And for the C, yeah, for A and C, it's the same, right? For those who contain A and C, so should be above A, right? The top is above A. The bottom is below C. So 3 and 3. The left is to the left of A. Right is to the right of C. So which is a 7. So it's 3, 3, 5, 7. So this is 3, 1, 5. So B and A are symmetric. So for those B and C, it's also a 3, 1, 5. And also, yeah, you should have noticed that if we have those who contain 2 of the grid, so should there be contain both all the 3 of the grid? Must be, right? So then finally we calculate those who contain A and B and C. So how many are there? So for A and B and C, so it should be on top of A, below the C, right of A, yeah, left of A, right of B. So it's 2, 2, 5. And then there becomes the basic inclusion and exclusion problem, right? So the basic logic of inclusion and exclusion it's a very easy to remember law. Is that 1 minus 2 plus 3. So for example, we want to calculate those contain at least 1 grid, right? So contain for those who contain at least 1 grid. So we just use those contain 1 grid, 1, minus those contain 2 grids, then plus those contain 3 grids. So this is the basic inclusion and exclusion law. So the answer for that would be, so maybe, yeah, I need a calculator to save our time. Is 735 minus 375 minus 315 minus 315 plus 225. Yeah, so it's 1305. Yeah, it's 1305. Yeah, sorry, no, 1305. Then, if you have those contain at least 1 grid, then contain no grid or no shade would be the total 2548 minus this 1305. So the answer would be 1243. Yeah. So this is the question. So we use the inclusion and exclusion to help us solve the problem. Okay, this is the last year's RMO round 2. Okay, and the similar question, this is a small question. So yeah, it's quite similar. So we want to calculate how many rectangles are there in this picture. So it looks very clear that it's the large rectangle remove 2 corners. So it's a similar logic. Maybe we can just, firstly, we just make the whole picture whole, right? So make the large rectangle whole. Because it's quite easy for us to calculate the rectangles in this large rectangles here, right? And then because this A, B, C, and D, right? So for this A, B, C, and D are what we put it in. So then we just remove those who contain A, B, C, and D. Then the problem is solved, right? So this is the easiest way for us to solve this problem. So firstly, after making it whole, so we just calculate the total number of rectangles, right? For total number of rectangles, so which should be 1, 2. So how many vertical lines? 1, 2, 3, 4, 5, 6. 6 vertical, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 horizontals, which means so the total amount of rectangles should be, right? Choose 2 from 6, then choose 2 from 11. This is a 55. This is 15. So it's 8 to 5, right? So the total number of rectangles is 825. Then we just remove those who contain A, B, C, and D. But here we should notice, right? Yours is different from my figure. How? It should be same. Yeah, it should be same. So what's the difference? So I just use the printed book. So this is the printed book. So I believe the picture are the same. Yeah. Okay, then we just remove those who contain A and B and C and D. But you notice that, yeah, an interesting thing is, so for any rectangle that contain A, right? So most of them must contain this B, right? So now in this case, maybe we just calculate those who contain B first, right? For those who contain B, or maybe we just contain A. Some rectangles are downwards. I don't know what's the meaning. So this is not a 6 times 11. This is 6 choose 2. It is a 6 choose 2 times 11 choose 2, becoming 825. They're not 6 times 11, of course. Of course not 6 times 11. Yeah. So I believe your picture is like this. So this is your picture, right? So I just make the picture the whole. Okay? So to help us solve the problem, so your picture should look like this, right? Of course. Then we just calculate those who contain A, contain B, contain C, and contain D. Okay? So now, first, for those who contain A, if you want to contain A, then we must use this line, right? So we must use this line to be the top, be the top length, right? We just be the top length. And then all the above, right? So all below can be the bottom length. And for the width, we must use this to be the left width, and all the right to be the right width, right? So if we want to contain this A, so the top and left, we have no choices. We can only choose the bottom and the right. So for bottom, we have 10 choices. For right, we have 5 choices. So there are 50 of it containing what? Containing A, right? And then for those containing B's, however, so for those containing B's, that's all what happened. Suddenly I cannot see the command. One. I refreshed it. A reflection. Okay. So for those who contain B, on the other hand, So there are two vertical lines, the two horizontal lines that's above B, but if we use this one, it must contain A. So for those who contain B, or middle sets contain only B instead of A, right? So to avoid some troubles. So we just use the second line to be the top. Then we can avoid those contain both A and B because those contain A we have already calculated. So for those who contain only B, right, we just use this one to be the topper. Then it contains no A's. So now topper and left is determined. For the bottom, we have 9 choices. For the right, we have 5. So we have 45 that contain only B. And then for C and D, they're symmetric, which means, so for contain D, also 50. And for those who contain both C and D, no, contain only C, are also 45. Right? So now we just contain A, contain only B, contain C, contain D, contain only C. So we avoid for those contain both AB and both CD, right? But however, this rectangle can contain, maybe we avoid both AB and both CD case, but they are still containing both BC and both AD, something like that, right? So contain, then we should check for those contain both AP and CD. So how many are there? Actually, there are 4. So because if we contain BC, right? So this is BC, BD, AC, and AD. Because they are at the end of the 2 grids, so only 4, right? So contain 2 corners, only 4. So these 4 are calculated twice. And so then the final answer would be, so the total 825 minus 250, 245, right? But we should add back this 4, right? Because these 4 triangles are calculated twice. So this would be the final answer, which should be calculator. So 725 minus 90 plus a 4. That's 639. Yeah, this should be answer. Okay, now this is about the question 27. Yeah, question 27. So question 26, 27, they're similar, right? So just use the inclusion and exclusion in figure counting and the combinatoric. They're similar in 2 distinct tests. Yeah, you should master this method quite well, I believe. Okay, so now we are facing the most difficult problems here, so which is about recursion or recursive counting. So recursion is the most difficult counting part, but yeah, each year the RMO and APMOPS will always have at least one question about it. So it's something about Fibonacci recursion, or maybe the passing ball recursion, yeah, or maybe like this 28. So this is what? So which year? 2019, yeah. This is a 2019 RMO problem, which is quite difficult. So it says that there is a number formed by 1 and 2. And then we use a way to transform the number into another by each one becoming 112 and each 2 becoming 111. So after we do the transformation, we notice that the first digit is exactly the same with the original digit. So the question is asking for how many times do 5 ones occur in the first 729 numbers. So what's the question meaning? What's the meaning of this question? Yeah, maybe we just make examples here. So for example, yeah, if the original number, yeah, it gives us example. Yeah. So the 2112 becoming 111, 112, 112, 111, standing for 2112, right? So the problem is, so how to write a 729 digit number, and after the transformation, the first digit are exactly the same. Actually, this one's too difficult, but maybe we start from the first one. Yeah, so obviously, the first one digit must be 1, because if the first one is a 2. Yeah, if the first one is a 2, then after transformation, it becoming 1, 1, 1. The first digit becoming 1, which is not equal, right? So the first one digit, it must be 1. Then, as we know, the first one digit is transformed, then in the new number is the first 3 digits. And the first 3 digits of the transformed and the original number, they are the same. So we use the first one number, we can determine the first 3 numbers. The first 3 numbers must be transformed by the 1, which is 1, 1, 2. And also, as the first 3 number of this Jones number is 1, 1, 2, then we should know the first 9 number of the transformed number as well as the first 9 digit of the Jones number. So this is the recursion logic, right? So we know the first 1, then we can get the first 3. And first 3 can get you first 9. First 9 can get you first 27. The first 9 is then 1, 1, 2, 1, 1, 2, 1, 1, 1. Then we can get into first 27, but I don't want to write it down because it's so long, right? So, but then we know the logic. First, we know the logic, right? So first 1 can lead to first 3. First 3 can lead to first 9. First 9 can lead to first 17, 27, and then everything else. So if you're okay with this logic, you type a 1 on the chat box. Yeah. If you're okay with this logic, you type a 1. Logic only. Here I see a 1. Yeah, what about a YouTube channel? Okay, I see 1s in the YouTube channel. Yeah, okay then. Move on. Yeah, move on. Yeah, following this way, we can just list out all the numbers here, right? All the numbers here, but yeah, I don't want to write the 729 numbers. It's terrible, and it's so easy to make mistakes. But maybe we can follow the patterns here. So maybe, right, instead of knowing the permutation of numbers, we can just determine the number of 1 and number of 2s here. So yeah, let's see. So how many? So for the first, right? So the first 1 number, 3 number, 9, 27, 81, 2, 3, 4, and 7, 2, 9s, right? So we just want to determine the number of 1s and number of 2s. So for the first one, we have 1, 1, and 0, 2. And so after each transformation, 1 will become a 1, 1, 2, right? So 1 becoming 1, 1, 2, which is 2, 1, and 1, 2. And a 2 becoming 1, 1, 1, so it's 3 1s. Which means the number of 2s in the second step equal to the number of 1s in the former step. So in the first 3 digits, there will be 1, 2, and 2, 1. So in the first 9 digits, we should have 2 2s and 7 1s. So for the first 27 digits, we should have 7 2s, and the remaining 20 are 1s. So for the first 81, we have 80 2s, and then the remaining 61 1s. And in the first 243, we should have 61 2s, and the remaining how many? Remaining 128 1s, right? So then we determine the number of 1 and number of 2s in the first several digits. But the question is nothing about this. But the question is asking about how do 5 consecutive 1s occur in the first 729 digits. So how can we get the 1, 1, 1, 1, 1? So we know that for any 1, right, 1 can be written as 1, 1, 2, 2 be written as 1, 1, 1. So if we want to see what? So if we want to see 5 consecutive 1s, it must be, right, a 2, 1 in the former number then it can only become 1, 1, 1, 1, 1, 2. This is the only way we make 5 consecutive ones, right? So there should be 5, yeah. As long as there is a 2 in the formal number, there is 5 consecutive ones in the letter number, right? Okay. So now, if we want to determine, so number of 1, 1, 1, 1, 1 in the first 729 digits, it's just referring to the number of 2 in the first 243 digits, right? So actually, so this question have a little trick. So it's not asking for the number of 1, 1, 1, 1, but you can just calculate the number of 2 in the first 243 digit, because you have to determine that. So as long as there is a 2 here, there would be a 1, 1, 1, 1 in the 729th. So now we see there are 61 2's in the first 243. So there must be 61 1, 1, 1, 1, 1 in the first 729. But actually the answer for this question is not 61, because in this number, right, in this number, we should notice that if we write it down, so we look at the end of each digit. So the first 1 digit ends with 1, the first 3 end with 2. So the first 9 end with 1, and so the first 27 should end with a 2. Why we look at the end of a number? Because, yeah, you would see. So the end is a 1, 2, 1, 2, 1, 2, right? So you would find out that for the first 243 digit, it ends with 2. It ends with 2. And if this 2 is on the last digit, right? So if the 2 is on the last digit, it can only make 1, 1, 1 instead of 5 ones. So now, actually, we have 61 2's, but one of it is on the last of its digit. So the last 2 cannot make 5 consecutive ones. But for all the 2's in front of it, it can make 5 consecutive ones. So then we use the 61 minus the 1 in the end. So totally, there are 62's before a 1. Then together they will make 60 consecutive 5 ones in the first 729 digits. So the answer is 60. This is a actually quite difficult problem. So it's a recursion logic. It's something like the Fibonacci rabbit problem, right? So you should notice that, so from each step, the first 1, first 3, first 9, first 27, so 1 will be transformed into 1, 1, 2. So the number of 2's is determined by the number of 1's in the former step. Yeah, this is the core logic. And you should notice that the 5 consecutive 1 is just based on the 2's in the formers. Okay, yeah, it's a bit complicated, but I believe so it's okay if you fail on this question in the real paper, because everyone, mostly everyone should fail. Yeah, that's it. Okay, then for the question 29, it's also a complex recursion problem, because the basic recursion problem, the Fibonacci recursion, right? So the stair problem, something like stair problem, the consecutive number problem, right? So we already finished the basic recursion in our book A. So in book B, we only have advanced problem. Okay, so if you have troubles in the basic recursion, please look back to your book A, right? You can find the YouTube video for the run through of the book A. So why do we stop at 243? Yeah, because we want to find the 5, we want to find number of 5 ones in the first 729. And this is determined by the number of 2 in the first 243, right? So you don't really understand. So which part you don't really understand? You don't understand the number of 1's and 2's, or you don't understand the relationship of 5, 1, and 2. Anyway, so we don't stop here, but you can think of the question on your own and look at the playback. Okay, question 29 is it's still a little bit difficult. So it gives us another rule is that, so originally there are red, yellow, and red balls. And for each operation, we just insert balls inside of it. So we insert a yellow ball to those with distinct color and insert a red ball to those with the same color. So because now for first step, we insert a yellow ball here and we insert a yellow ball here. So this is the first operation. And then, so the second operation is to insert yellow here, red here, red here, yellow here, right? So this is about the second operation. And the question is, after the seventh operation, how many, right? After seventh operation, how many red balls are there? So yeah, actually I give you a mercy. So the original question is about the 10th. So when I use this question in China mainland, so this should be 10. But yeah, in Singapore, I made a mercy to turn it into 7. So why this is a mercy? Because for 7, I believe you have the possibility to list it up. You use the enumeration to use the 1, 2, 3, 4, 5, 6, 7, right? You just list it up to get the answer. It's okay, as long as you don't make mistakes. Yeah, it's okay for you. But still, it's a bit complicated, right? It's a bit complicated. And for this question, yeah, we must, right? So we must find the relationship between the red balls and yellow balls between each of the steps, right? Between each of the steps. So if we just list the number of red ball and yellow balls, actually you can get the answer, but the answer may be, just maybe, right? Just maybe a little bit complicated. You may not that easy to find patterns. But yeah, the actual pattern is not based on the number of balls, but actually the number of pairs. So how to determine the pairs? So we just treat two adjacent balls to be called a pair. So now the first row we would have 2 pairs. The second row we have 1, 2, 3, 4, 4 pairs, right? So now in each operation, we insert a ball inside each of the pair, which means we make 1 pair into 2 pairs. Then we should get after the nth operation, totally would have, right? So 2 to the power of n plus 1 pairs of balls. Then for 1 pair of ball, how many different color combinations should there be? So it should be it can be 1 red and 1 yellow, 1 red and 1 red, 1 yellow and 1 yellow, right? And let me see. So after each of the operation, right? After each of the operation, if the original pair is white, right, yellow, we just insert 1 yellow inside, becoming white, yellow, red, yellow, yellow. So for yellow, yellow, it should be made into red, yellow, red, yellow. And for red, red, it will become red, red, red. Which means after each of the operation, a 1 yellow would be making into 1, sorry for that. So 1 yellow, what happened? What happened? No, my pen is not working. Yeah, so we would see that 1 yellow would make 1 red yellow would make into 1 red yellow and 1 yellow yellow, and 1 yellow yellow would be made into 2 red yellows, right? What about red red red? So there cannot be red and red, red red red, because and red red must come in from original red red. So originally there is no red red, which means in the end there will be no red red. So there will be always not be red red. So we just want to calculate the number of red yellow and yellow yellows in each step. And this recursion logic is quite easy, right? So in the zero, so in the zeros, so it's the original one. So we have 2 red, yellow, 0, yellow, yellow. After the first operation, so 2 red, yellows becoming 2 red, yellow, and 2 yellow, yellow. And the total 2, 4, 8, right? And then in the second step, we should see that 1 red, yellow becoming the 2 red, yellow become 2 red, yellow, and 2 yellow, yellow. And the 2 yellow, yellow just becoming 4 red, yellow. So it's 2 and 6. So then we can see, so the number of yellow, yellow in the second step equal to the number of red, yellow in the first step. So this is logic of recursion. So this recursion is just the similar logic as this 1 and 2 stuff, right? So the number of yellow, yellow equal to number of red, yellow in the former step. So in the third step, totally 16 pairs. So you would have 6 yellow, yellow, and then 10 red, yellow. And the fourth step, so the number of yellow, yellow pair equal to the number of red, yellow pair in the former step. So 10 and 22. And the fifth step, totally 64, 22 here, then 42 here. Then there's 42 here, totally 182, which makes it 86 here. And then 86 yellow, yellow, and then how many red, yellows? How many red, yellows? So 2, 5, 6. So which makes it to be 1. No, 1, 7. Yeah, this is what? No. This is a what? This is 170. Yeah, 170. So now we just know. So how many pairs are there in the after the 7th operation, right? This is not the number of balls, right? This is not the number of balls. But now we should use the number of pairs to determine how many number of balls are there. Actually, it's not that difficult. So we look at this. So we know that, so for each of the layers, it will always start with red, and several yellow, several red, several yellow, several red, something like that, right? So then we should notice that, so the first 2 pair is always red and yellow. And except for this, as there's no red, so red is always adjacent to yellow, which means, right? So here we have 1 balls, or 1 red ball should belong to 2 pair of red, yellow, because 1 red must be adjacent to 2 yellows. So 1 red ball belongs to 2 red, yellow pairs, except for this 2, right? For top and bottom. The top and bottom red only belong to 1 red, yellow, and those red in the middle belongs to 2 red, yellow pairs. Then in this 170 pairs, right? So 170 pairs, we just remove the first and last 2 pairs. And then each of the 2 pair determine 1 red balls divided by 2. Then plus back the top and bottom 2. And the answer is 86 red balls. Now this is a little bit complicated problem. Also, like this RMO1, it's a complicated recursion. So this is the most difficult question about recursion you may face. Okay. And then, then the last one, question 30. So the question 30 is a very classic Catalan problem. The Catalan problem have another name, which is called the stair notion. Have you ever learned this before? Yeah, if you learn this type of question, the Catalan problem, the stair notion before, you type a 1. If you haven't, you type a 2. Yeah, I want to make a survey here. No, maybe the environment in Singapore. Have you learned about this question before? Yeah, if you have learned type 1, if you haven't, type 2. Okay, I see a 2 here. I say 2 again. I say no again. Okay, I believe all of you haven't learned this before, right? So the Catalan problem, yeah, includes many, yeah, actually include many of the problems. So the basic thing is something like, Teacher Nicole, you're in primary 4. Yeah, no wonder if you're in primary 4, it's very tough for you to enter RMO. Yeah, mainly is about primary 6. So no wonder, yeah, if you're in primary 4, no wonder you haven't learned it. Yeah, okay. So now the Catalan problem is just to transform a certain type of problem into the number notion problem. So there are several typical questions, but the time is limited, so I don't extend it here. So maybe I just focus on this question. So we want to make 1 to 12 into a 2 times 6 rectangle. And we want to make sure that so each number below is larger than above, and the right is larger than left. So here, yeah, it's easy for us to list some of the possible ways. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So this is the way we satisfy the need, right? So this is an example. Yeah, this is an example. But it's asking for how many ways are there. So maybe, right? So instead of filling the number directly, we change another way. So you know how the way I write these numbers. You notice? So I write the number directly from 1 to 12, right? From the smallest to the largest. So then we change the way of, yeah, we just change the ways of writing numbers. So firstly is that we write 1 to 12 in order. So first we write in a 1, then a 2, then a 3, then a 4. Now you would see that there are 2 rules. So the first rule is that for each number written, we have 2 choices, right? So each number, we have 2 choices. Why 2 choices? We can only choose to write it on the top or bottom. Because, right? So now you see, for example, I write 1 and 2. So if I want to write the 3, so the 3, if 3 have only 2 places to choose, right? So this way and this one. We cannot write it maybe to the right grid. We must write it on the most left grid of either column, either row, right? We can only choose the row. We cannot choose the column because we must write this number to the most left column. There's no other choices. So that's why I say when we fill in the number, we only have 2 choices. We either write it on the top or the bottom. We cannot choose the column. So okay for this? If okay for this, you type a 1. Yeah, if okay for this, you type a 1. So this is the first law, right? So this is the first law. And the second law should be what? So now we ensure that in each row, left is smaller than right there, which is quite good. Then how to make sure that the top is always smaller than bottom? Right, how to make sure the top is smaller than bottom? Yeah, now for this way is that when we write the number down, so during the whole process, during the whole process, so the number on top must always be no smaller than number on bottom. Why is that? So for example, right, when we write this 1, so 2 rows are empty. So we can only put 1 on the top instead of the bottom. Why? Because if we write 1 to the bottom, how do you write this? It must be some number larger than 1, which is not correct, right? So, and then for 2, I can write 2 either here or here. But however, so if you write 2 here, so we have both 1 numbers on the top and bottom. And for the 3, you cannot write 3 here. Because if there is 3 here, so how do you write this one? So in each of the cases, so if we have a number, right? If we have bottom more than top, so we would always have 1 top grid, have no number to fill in, right? Because we fill in the number from the smallest to the largest. So which means if the bottom exceed top, then there will always be 1 grid. We have larger number on top than bottom, right? So during the whole process, we must make sure the numbers on top always, no smaller than number on bottom. So how to make sure that the number on top not exceed to the top and bottom? So then we can use the number notion way to help us solve it. How to use the number notion way? So we use the number notion to express the way we fill in the numbers. We know, so there are 6 numbers on the top, 6 numbers on the bottom, which means we should write in 12 numbers, 6 to the top, 6 to the bottom. So now we just draw a 6 times 6 square. So what does this square referring to? So this square is the way we just take note of the ways we write numbers into a table. So firstly, so we start from this point. And if we want to fill in a number, right? We want to fill in a number on top. We just, we put a piece here. So if we want to fill in a number on top, we move 1 step right. However, if we want to fill in a number to the bottom, we go 1 step on top. And then, so after we fill in all numbers, which means we just fill in 6 numbers to top, 6 numbers to bottom, we should go 6 step right, 6 step top. Then we will reach the top right of the square. And it's following a shortest path, right? It's following a shortest path because we never make step back. And here we would see that each of the shortest path, each of the shortest path, for example, I draw it this way, right? So each of the shortest path referring to exactly 1 method of filling in the numbers. So let's see. So for example, I draw a path here, right? The blue path. So what does this blue path represent? So we just notice the steps. So first step, we go right, which means we fill the first number on top. And second step also right, so we fill the second number on top. The third step is bottom, so we write the third number to the bottom. Fourth number to the bottom. Fifth number, top. Sixth number, top. 7, top. 8, bottom. 9, bottom. 10, top. 11, bottom. 12, bottom. You see, each of the shortest paths I draw on this picture referring to each way we fill in the rectangles. So now the question becoming, how many distinct ways, how many shortest paths are there to start from the top to the end, right? To the bottom to the end. So how many ways are there? So if just the number notion, yeah, we just use, maybe we can just use the choose 6 from 12 to get it, but not for this, because we have the rule is that we want to make sure that during the whole path, we want to make sure number on top always not smaller than number on the bottom, which means, right? So in this picture, there are, so each point referring to the steps we have gone already. So if we want to make sure that this thing never happened, right? We want to make sure this thing never happened. So there are some point we cannot reach. Which point? It's something like a diagonal. So for example, this one. So this one means we write one number on top, but no number on bottom. Sorry, one number on bottom, no number on top. Not correct. This one, this one, this one, this one, this one. Notice that this 6 point, right? This 6 point is exactly the bottom number is greater than the top number. Or which means this, the whole zone, right? So this whole zone, all the point in this whole zones is not able to use, right? So if we go into this zone, which means the bottom should be larger than top, which makes some mistakes. So, which means the shortest path for us to go is limited in the down, this right down zone, which is something like a stair. You see? So this is exactly something like a stair. So this is why the Catalan problem is called the stair notion, right? So which we can only go to the in this stair-like zone. Then the problem is, so we just do the number notion. So we have 1, 1, 1, 1, 1, 1, 1. Then 1, 2, 3, 4, 5, 6. Then this is an 2, right? 5, 9, 14, 20, 5, 14, 28, 48, 14, 48, 48, 19, and this is an 48, 1, 3, 2, 1, 3, 2. So totally how many methods there? It is 1, 3, 2. Let me check. So there must be, I don't know if I do it correctly, so I should use another method to check. So actually for Catalan problem, there is a combination number to just referring to it, but this is a 6 to 6. So it's right, and then divided by, yeah, I must make something wrong. I must make something wrong. No, yeah, it's correct. It's correct. Yeah, it's correct. It's correct. So now this is the so-called Catalan problem. So if you haven't learned Catalan problem yet, so it will be a little bit difficult for you, but I think you should know about this. These are famous questions. Okay, yeah. Set for the things you haven't learned yet. Yeah, but I believe the counting, right? So counting, this is the maybe the most difficult 10 questions in the RMO and APMOPS. So I believe for counting part, you may just go back to book A, right? So you make sure that you can handle. No, we don't plus the 42. Yeah, Keegan, we don't plus 42 because the 42 cannot go here. So at this point, the goal can only be reached by this. Yeah, you know. Okay. So yeah. What did I say? So you can just go back to book A to check all the basic question type, to master all the counting problem in the book A. So if you can get all questions in the book A correct, I think you graduate from countings. Okay, now that's all for this week. Next week is about the geometry, right? Geometry would be more familiar with you because I believe all of you have learned all you need for geometry. Okay, so unlike counting, so I believe many of you haven't learned some knowledge about countings. Never mind. Okay, see you next week. Bye-bye.